Now, so from this point onwards, I'd just like to tell you that we'd like to know the combination of springs, okay? So let's write combination of springs and first we're going to look at series and then parallel. Series basically means that you got one spring connected like this, the other spring connected like this, and then you have a load or a force acting here. This spring is K1, this spring is K2, suppose. That's the spring constant, right? So I just want to tell you that in series, the force in each spring stays the same. And however, the extension may differ. So by that we could say that the total extension x can be written as extension in the first spring and extension in the second spring, and it could be like 1,000 springs, doesn't really matter. Now, since we know that, I'll do it with a different color. Since we know f is equal to kx, then k is equal to f upon x. So with that said, you just need to remember that this would be f over x, this would be, oh my gosh, sorry, x will be equal to f upon k. So this will be f over k, this will be f upon k1, f upon k2, because force is the same, right? So f is the common thing, you can cancel it out. Ultimately, you're gonna get something like 1 upon k is equal to 1 upon k1 plus 1 upon k2, and so on, right? So this is a general formula to find the extension of springs in a parallel system, where you just need to understand where k is the combined stiffness of a spring system. Spring system means no matter how many springs are like put in together like that, okay? If you have any questions, do let me know, okay? Alright, now however, in a parallel system, so a parallel system that is pulled together was like this. There's something like a plank or something, and then we're pulling it down together. a second, let me just, okay. So suppose that this is K1, this is K2. So in parallel system, the main difference is that the forces are now divided. Each one basically picks up a different force, okay? But the extension is same because it's being pulled together, okay? So we can write that the extension X remains same as it is pulled together. Okay. With a force F. Now we can also remember that where the force F in each spring will be different. That's what you guys need to remember, okay? Now that would mean that the total force would be something like, F equals to F1 plus F2 plus no matter how many springs are in parallel. Now, since we know that F is equal to Kx, so I can just put it here. So there will be Kx, this will be K1x, this will be K2x, and so on. So you can cut off x because the extension in the system is the same. So ultimately, you're gonna get K equals to K1 plus K2 plus K3 maybe, right? And so on, whatever. So obviously, you just need to remember that where the K is combined stiffness of the system. That's what you guys need to remember, okay? Please let me know if you understand this. Javeria, how are you? You didn't come yesterday, why? Javeria, are you there? Now, okay, now let's go on. So what I really mean by this is, if you basically understand that if I make two different, systems right here, like this, and like this. Wait a second, please. Like this. Now here let's keep force, and here let's keep extension. Again, force and extension, and you have like two different graphs, right? So suppose K1 is stiffer, it has greater gradient. K2 is less stiff, it has less gradient. Same goes for the other one. K1 is stiffer and K2 is basically less stiff, right? So what you need to understand is that in a series system, because they will feel the same force, which means that if I start from this side, so the force is the same, which means a stiffer spring shows this much of extension, x1, but a less stiff spring shows a much greater extension on the same force, and you can adjust that to get the full extension, right? Is it clear, Aman? Do you understand this?
Yes, sir.
Okay. But in a parallel system, you're basically making them go through the same extension. So a less stiff spring requires a smaller force to show that, and a more stiff spring would require a greater force, which means this will have force F2, this will have force F1, right? So both will basically have different forces on them. So that's what you guys need to remember, okay? So what you can basically comment on this is that in this K2 is less stiff. So for same force, it shows greater extension. Okay. And in this one, K2 is less stiff. So for same extension, it requires less force to be applied, or it shares less portion of that force. What you guys need to understand, okay? All right, now, okay, you can please write this down, draw this, and then we're going to start a question that we basically need to do. Okay, now, so now what they do is they're like, okay, draw, for example, they've given some drawings to you. So they say for each arrangement shown, find number one, total spring constant, which means combined spring constant, and number two, spring constant in terms of K, and total extension in terms of E, and they've said that each spring has a spring constant K and total load L. Okay, so they've given this. So first drawing that they've shown is it's like this. One spring and the other one like this, right? So they say the load is L and they both have the same spring constant like this. The second drawing they have shown, well, okay, let me just do it on this side because two are fine actually. Two. So that would be like this, which is and so here's the load, and this one has K, this one has K as well. Okay. And then let's go to the third one. The third one is like so there's a spring like this, there is a spring like this, and then there is a spring like that, and then it has a load on it. All of them are K's. And the fourth one is like that, and then another like that, and another like that. Okay, and the load here is L, this is K, this is K, this is K, this is K. Alright, now we're gonna solve this one by one and see how to manage these if they come in your exam. Okay, I hope you guys have drawn it, so we'll go to the first one then. First of all, let's look at the total K. Okay, so we want to find that. So for total K, what I'm going to do is, I'm going to say, okay, because this is a series system, and I know in series system, the K is given by 1 upon K equals to 1 upon K1 plus 1 upon K2. So the total K is going to be 1 upon K plus 1 upon K, because both of them have the same, right? So this will be then 2 upon K, and then K total is going to be K upon 2. So first we solve this, okay? So in terms of K, we just found this, and now we want to find the total extension. Okay, so we are going to total extension. Now for total extension, we already know that actually force is equal to Kx, and because force is equal to Kx, this F is L, K is now K by 2, and this is the total extension we need, right? So that would mean that the extension is equal to 2 times L over K. So we got to remember this, alright? Now think about it this way, right? the total extension in anything that is E, alright, got to be, okay, in fact, wait a second. Wait. Total, we need to basically remove L somehow so that we get this. This would not be the right way of doing this. That would be too easy then. I just want to tell you that for each spring, basically, the extension, like in the first one, in the first spring, we could say that would be load over K, because it has a spring constant and the force is the same. And then for E2, it would be the same, that load upon K. And then because the total extension ET is equal to E1 plus E2, because we know that in series system, basically they're the same. So then what you're going to do is you're going to write load upon K plus load upon K, alright, like that. So because it says that we need to find total terms in E, just E, right? So think about this way. This can be written as 2 times L upon K, and because if you remember, L upon K is basically just E, like any E could be L upon K, so the total extension will be equal to 2E, just like that, because the extension was E. Is it clear, everybody? Any questions? Now, wait a second, please. Similarly, there's like another way, the other one where it says this one we can do total K. Because this is a parallel system, so in parallel system we already know that K is equal to K1 plus K2 and so on. So in this one, the K total will be equal to K plus K, which is just 2K. So that's our answer here. And now we would like to find the total extension. So one of the easier methods to do this is, now look at this. So we already know that in this one, force is equal to Kx. The force is L, K is K, and extension is E in its spring, which means that E is equal to L upon K, like that, right? Now, so now when you combine this, and then for a single spring, when you combine, what will be the effect on total extension? You can again basically use F equals to Kx. Now this time the force total load is L, K itself is 2K, and the extension is the total E, right? So if you look at it, the total extension is going to be L upon 2K, where L upon K is just E, which means it comes out to be half times E, and that would be your answer. So it means that if you put something in parallel, the total extension of the same springs is going to be halved, because the force in each spring is going to be halved. Is it clear, everybody? You could have done the same thing with the previous one. I just showed you 2 different ways how to do it, but I think the later one is better. Okay. Javeria, Hamad, Aman, Aisha, is it clear?
Yes, sir. Yes.
Okay. Then let's check out this one, right? Now for this one, I would want to find first the total k. Now if you look at this system, always basically solve the inner system first. So we're going to solve this first, and then we're going to combine and solve these two together. So that's how you work it out, okay? So first the inner system, okay? For the inner system, what I'm going to do is I'm going to find, because it is parallel, so the k in parallel will be k1 plus k2 and so on. So the k in parallel will be k plus k. So after 10 minutes please rejoin, okay? So this is going to be k in parallel is equal to 2k, alright? And now what you're going to do is you're going to find this, the part 2. So this was 1, and now you're going to look at 2. So for 2, you got 2k and k in parallel, so in series, which means 1 upon k total is going to be 1 upon 2k plus 1 upon k, because 1 is k and the upper one was 2k. And now you're going to take reciprocal, which is going to be 2k. So this is gonna be 1 and this is going to be 2. So that makes it kt equals to 3 by 2k, right? So the k total here will be 2 upon 3k, and that's what you needed to find. Understood? Interesting.
Sir, how did you solve this? Can you do it again?
Yes, why not? So what I did was, Aisha, first I looked at, always try to solve the inner combination first, right? Inner combination is the first combination, that's the parallel one, right? So what I did for the first one, I know that in k in parallel is simply added up. Do you understand? All the k's are added
Yes.
up. So that would mean the k in parallel is 2k, which means this section where 1 is written, the combined spring constant of this is 2k, right? Then for the second combination, which is the series one, which means in this one it was 2k and in this one it is k. So the combined here would be, in series you have to take reciprocal and add it. So for the first one it is 2k, and for the second one it is just k. Do you understand?
Yes.
Okay. Now what I did was I just took reciprocal. I took LCM. You can do it with a calculator as well. So then this will be 1 and this will be k will cancel out, 2 will remain. Understood? So then Aisha, it's going to be 3 over 2k. When you take the reciprocal to find the k total, it is going to be 2 by 3k. Do you understand?
Yes.
If you guys ever feel difficulty that, okay, I don't understand what 1 by 2 and 1k is, so what you can do is you can simply divide 1 by 2, like you write 1 divided by 2 and then you just add 1. So it is going to give you 3 by 2 like that. Understood?
Yes.
Okay, now, so since we got the total spring constant of the combination, so we can actually then go towards the total extension. Now for total extension, for just one spring, if there was one spring, we know that F is equal to Kx. For one spring, the load was L, K was K, the extension was this. So which means the extension is L upon K. We already know this for just one spring. So now you use F equals to Kx. The total load is L. The combined spring constant is 2 by 3k and the total extension is Et. So which means Et is going to be 3 over 2 L over k. So now just replace this right here. So it would be 3 by 2 E. Is it clear? you get my point? Okay. Please have a look at it and see if you guys understand this, because this is okay. Okay, now let's look at the last one. Okay. For the last one, first of all, we'll solve this one, the first inner one, and then we're going to solve this one, and then we're going to combine these two. Do you understand this? That's how we're going to get the whole k there. Okay, now let's do this. So for the first one, let's write here total k. So for total k, I'm gonna do, you see, for the first one, k is in parallel, so it is going to be k plus k, that's going to be basically 2k. In the second one, it is also in parallel, so it is k plus k, that is going to be 2k. Now, if you look at it, when you combine them in the third step, when you combine both top and bottom springs, because they're in series, so I can write k total would be then 1 upon 2k plus 1 upon 2k. So the k total is going to be 2 upon 2k, which is basically just equal to k. Is it clear?
Did you cancel something out to get the k?
No, I just cancelled 2 over 2, na?
Oh yeah, okay, yeah.
Now, we're going to find the total extension, and for total extension, first of all, for just one spring, I know that F is equal to Kf. If there was just one spring, load was low, K was K for it, and extension was E. So extension is L upon K, we know this. Now, let's go forward. Again, for the whole system, we're going to use this. The load was L. This time the K total is also K, and E will show this one. So E total is L upon K actually. Because L upon K is just the same, so in this one, E total will just be E. Now the interesting thing is that the fourth combination basically acts just like it is one spring. Although there are four, but because of the series and parallel combination, it just acts that we have just put one spring altogether, not many. Understood?
Yes.
Okay, please write this down. This is very important. So generally, what I would suggest is that usually you will get combinations like these, and when you do, you can quickly comprehend that if you look at the first one and the second one, which is the most basic combination, and from these combinations more combinations can be formed. So you see anything in series, like two spring in series, will always give you double the extension for the same load, and for parallel it would give you half the extension for the same load, and then of course you can use them here as well, and that would help you, achieve whatever you want to. Okay, so that's just a tip for you. Okay. Now I believe that we must, stop like today here, because whatever we want to do next will take some time, and I don't want it to just be left in the middle. So it would be best if we just stay here. If you guys have any questions, please let me know. Okay. So I guess I'm gonna see you people in the next class then.